Hello students, in the previous video related to structure of atom, we had studied a few concepts, say how to fill the electrons or which rules has to be followed to fill the electrons in the respective orbitals. So we studied Aufbau principle and Pauli's exclusion principle also, isn't it? Now we will study next rule, that is Hund's rule. HUNDS, Hund's rule of maximum multiplicity. What Hund's rule states is, I'll just put it in simpler words first and then we will write the statement for this law or this rule. Hunt states that, or he stated that when you are filling electrons in the orbital of same energy or energy of the orbitals if it is same, for example, now s orbital, in this you are going to fill the electrons. Say for example 1s. In 1s, however, we don't have this problem related to Hund's rule, because however if there are two electrons, once we fill the electron and then the other electron we fill in it like this. Whereas it can be explained in a better way in p orbitals or d orbital. So in p 3 subshells you have, in d 5 subshells. Yes, in p orbital, say 2p orbital, you have orbitals of same energy. Orbitals of same energy. Now in this case, when we have to fill the electrons, maximum of how many electrons can be filled according to Pauli's exclusion principle? In a single orbital, maximum 2 electrons. In a single, 2 electrons. So in P, total of 6 electrons. In D, how many orbitals we have? 5 orbitals we have. So in that 5 orbital, 2, 2, 2, so 10 electrons we can fill. According to Hund's rule, he said, while filling the electrons, if suppose it is 2p4, how to fill the electrons now? So filling the electrons, 1 electron, then again writing 2 electron, this will be wrong according to Hund's rule. He said that the pairing of electron in the orbital of same energy will take place only when all the available orbitals are singly occupied first. First you have to go on filling the electron single, and only then if there is remaining electron, then the pairing will take place. So how should I write this? This is wrong now. So 3 orbital, so 4 electrons we have to fill, 1, 2, 3. So a clockwise direction, and then it need not be like all clockwise, yet we do follow this standard method of writing. And next will be of opposite spin. You remember in Pauli's exclusion principle we studied. So now 4th electron goes where? Here. Now the pairing takes place. Pairing how? One is spinning in a positive direction, the other one in the opposite direction. So this is what Pauli's exclusion, Hund's rule of maximum multiplicity states, that when there are orbitals of same energy, then the pairing of electron can take place only after each orbital is occupied singly. So just write a statement for this. How do you write? Among the orbitals of same energy, states that among the orbitals of same energy, electrons do not start pairing until all these available empty orbitals are occupied with single electrons. With single electron. Hope it is clear. So what does it state? Among the orbitals of same energy, the pairing of electrons does not take place until all the empty orbitals that are available are filled with single electrons. This is Hund's rule of maximum multiplicity. Now next, when we write the electronic configuration, then you should be knowing to follow all these rules. Which are they? Aufbau principle. Aufbau principle, you remember, after 1s, 2s, 3s, we wrote it using a diagram in the order you can remember. The other one was Pauli's exclusion principle, which states that no two electrons can have all the 4 quantum numbers same. At least the spin must be different. So when you fill, you can't fill the electrons this way. In one orbital, the electrons both having positive spin, you cannot fill. You will have to fill one with opposite spin, directing in the other way. So sometimes they write it this way also. This is also the right way of denoting the electrons, not a problem. So however, this is mentioned in your text, so not to get confused, I have written that. And the next principle that you have to remember is Hund's rule of maximum multiplicity, where first you have to fill the electrons. One single electron must fill the orbitals, and then the pairing will take place. We will start writing electronic configuration. Since the base of inorganic chemistry is where you learn to write the electronic configuration, I'm giving much time for it now. So this is the end of this unit where you will be studying about electronic configuration. Very important again. Electronic configuration of atoms. What do you mean by electronic configuration? Electronic configuration means filling of electrons in the orbitals. The respective orbitals is called electronic configuration. So in the given orbital, you will be writing or you will be mentioning of how the electrons gets filled up there. That is electronic configuration. There are two ways of representing this electronic configuration. So one way is, what is electronic configuration? Distribution of electrons in the orbitals of the atom. We call it as electronic configuration. The two ways of representing this electronic configuration are, one is SPDF notation, one is SPDF notation, and the other one is called as orbital diagram. SPDF notation and orbital diagram. So we will start writing the electronic configuration. Before that, we will write down few atoms, that is elements with its atomic number. Now you know what is atomic number? The number of protons or total number of electrons or number of protons present in the atom. Starting, we'll be writing for hydrogen, where the atomic number, that is Z, is 1. Then comes helium 2. Then lithium 3. Beryllium 4. Boron 5. Carbon, nitrogen, oxygen, fluorine, then neon. For these, we will be writing the electronic configuration. It is easy. We will try to write in SPDF notation as well as orbital diagram. First, let me start with hydrogen. How do you write the electronic configuration for hydrogen? SPDF notation. You know how to write by SPDF notation. Aufbau principle, you remember? 1s, 2s, 2p. Using this. Okay, we'll see how we can write it. Now 2p. This is according to which one? This is according to Aufbau principle that I have written. And 5. So here one more, 7p. Now how do you write? Let us just make a mark and keep so that you can remember it better. First comes 1s, then 2s, then 2p, 3s, 3p, 4s, 3d, 4p, 5s, then 4d, 5p, 6s, 4f, 5d, 6p, 7s. However, we are not going to write all these large numbers electronic configuration. So these many, if we know, it's more than enough. So we shall write the electronic configuration for hydrogen. Hydrogen means atomic number is 1. That means one electron has to be filled in which one? 1s, which has lower energy. So 1s, how many electron is getting filled? 1. Okay, one more point that you have to remember. One thing you should have idea about atomic number, this order, and then Pauli's exclusion principle, Hund's rule. Other than that, in s orbital, okay, I'll write this way. S orbital, maximum of 2 electron, p orbital, maximum of 6 electron, d orbital, maximum 10, f orbital, maximum 14 electrons can be filled. This also you remember. Okay. So with all this we will start writing. 1s, in s orbital, how many electron? 1. So 1s, 1. This is SPDF notation according to this notation. In another way, orbital diagram, how can you write? Orbital diagram for s orbital, we write this way. 1s. How many electrons here? 1. So 1 electron we denote. Hope it is clear. Remember this also. S means you denote it this way. P means with 3 orbitals. D means with 5 orbitals. F means 7 orbitals. This is for F orbital. Clear? Now we will write hydrogen is done. Next, helium. Helium atomic number is 2. So how do I write its electronic configuration? Again in 1s. That means one extra electron is added. Where it adds? 1s, 2 it becomes. 1 plus 1, 2. So how should I write the orbital diagram here? There was one electron already. Now one more electron has been added. So helium 2. Next, lithium. Lithium atomic number is 3. So already 1s2 has been filled. So where do the electron go now? Electron goes to next one. Which is the next one? After 1s comes 2s. 2s. Already 2 electron has been filled here. So one more electron will go to 2s. So 1s to 2s 1. How should we write the orbital diagram? 1s, in 1s 2 electron, in 2s 1 electron. So total 3 electrons in case of lithium. Now next we shall move on to beryllium. Okay, beryllium atomic number is 4. How should I write? 1s2, 2s. See, here in S maximum 2 electrons. One more electron we can fill. Here itself it gets filled up. So how should I write orbital diagram? Your 1s, 2s, in 1s 2 electron, 2s, 2 electron. Now don't get confused that she had told something about filling of electrons. Why she is not filling single and then pairing it up? Because this is a different orbital, this is a different orbital, and that Hund's rule is for the same orbital. See, P, D, F and all, you see same orbitals, that is same subshell with different orbitals. There you consider it. Next, boron. Boron is 5. How should you write? 1s2 is done, 2s is done. Next the electron goes to 2p. So 1s2, 2s2. How many electrons? 2 plus 2, 4 is done. Last one electron goes to 2p. 1. You understand the order? After 1s, 2s. After 2s, 2p. After 2p gets filled up. In P, how many electrons can fill? 6 electrons. So up to 6 electrons you can go on filling after this. Then comes 3s. Okay. Now 2p, 1. How should I write the orbital diagram? 1s, 2s, 2p means 3 orbitals. So in 1s, 2 electrons, 2s, 2 electrons. In 2p, 1 electron. So 1 electron you will fill this way. Next, after boron, carbon. Carbon is 6. What is the electronic configuration? One more extra electron. This was 5. One more has to be added. Where it will be added? To the p orbital itself. So 1s2, 2s2, 2p, 2. 2 plus 2, 4, 4 plus 2, 6. 6 electrons fill in this order. How do you write the orbital diagram? 1s, 2s, 2p. In 1s, 2 electrons, 2s, 2 electrons. Now you see 2p2. So 1, should I write one more there itself? No. Single we have to enter in the next available empty orbital. 2p2. Next comes nitrogen. Nitrogen atomic number is 7. 1s2, 2s2. Here you see 2p2 was there. Now one more electron, so 3. 2 plus 2, 4 plus 3, 7. Orbital diagram. 1s, 2s, 2p. In 1s 2 electron, 2s 2 electron, 2p 3 electrons. So 3 electrons should occupy the empty orbital first, single, and then pairing has to take place. Now the next electron which will be entering will get paired up here in the next element. Okay. Next comes oxygen, 8. How do you write the electronic configuration? 1s2, 2s2, 2p, 3 plus 1, 4. 4, 5, 6, 7, 8. Now 1s, 2s, 2p, 2, here 1s, 2s2, 2p4, 1, 2, 3. Single it has occupied. Now pairing has to take place. Where pairing will take place? Available lower energy, this one. You know this, isn't it? This is 2px, 2py, 2pz. In d orbital, dxy, dyz, dzx, dx square minus y square and dz square, those orbitals. Now oxygen is done. Fluorine, 9. 1s2, 2s2, 2p, 4 plus 1, 5, isn't it? 8 plus 1 electron extra. So 1 electron in 2p, 5 it occupies. One s2, 2s2, 2p5. So 1, 2, 3, 4, 5. Clear? Neon, 10. 1s2, 2s2. Still one more electron can get filled here, isn't it? 2p, because p can accommodate maximum of 6 electrons. So 2p, 6. How should I write the electronic configuration? 1s, 2s, 2p. So 2, 2, here 6. 1, 2, 3, 4, 5, 6. Here you observe for nitrogen, I'll explain it again later. Nitrogen, you see, only half filled, exact half filled. Maximum how many electrons can occupy? 6. Out of 6 electrons, 3 electrons. That means exact half has been filled. Remember, I'll tell about it later. Why? Now you know neon. What is neon? Neon is a noble gas. What happens here? Noble gas. See here, all the shells are completely filled. When they are completely filled, what happens, you know? They don't want to react with any other substance. They don't want to show their reactivity, and that is why they are called as noble gas. Helium, neon, argon, krypton, xenon, these are all called as noble gas because all the orbitals are completely filled. If they have to react with any other substance, what they have to do? They have to give their electrons, or they have to take the electrons if they don't have. That is how. But here, since they already have, they are stable. So they don't want to change their stability. That's why they either don't donate nor accept the electrons, and hence they are called as inert gases or zero group elements. They are called as. They are called as noble gases. They don't react with any. That is what it means. Okay, after this comes, this is a noble gas. Till 10 we have written. Next comes sodium. Sodium symbol is Na. Atomic number is 11. How should you write? Here, noble gas configuration. 1s2, 2s2, 2p6. Now 10 is done, isn't it? One more. Now where does it go? After 2p6 it goes to 3s. How many electron? 1 electron. So when you write, how do you write? 1s, 2s, 2p, 3s. S means always one box. I mean box in the sense orbital, okay? 2s2, 2p6. 1, 2, 3, 4, 5, 6. 3s1. This is how. Now the important term that we will be studying is, see, this can be also written this way. Noble gas is a standard one, isn't it? So we also write it as neon configuration into 3s1. Why? Neon is a completely filled element where all the electrons are filled in all the orbitals. It is stable, so we take that configuration and we write the other remaining electrons this way. And this completely filled shells are called as core electrons, or the shells are called core shells and the electrons are called core electrons. Core means inside. Core electrons. These electrons, see here the principal quantum number is high. The one having electrons filled in highest principal quantum number apart from core electrons are called as valence electrons. Remember this. Now if they ask you how many valence electrons are present in sodium, how many valence electrons? 1 valence electron. Next comes, after sodium comes magnesium. Magnesium is 12, isn't it? How do you write the electronic configuration? 1s2, 2s2, 2p6. So neon into 3s, one more electron can be filled, 3s2. So if I ask you to write the orbital diagram, you can write however. So if I ask you how many core electrons are present in magnesium, you will have to say 10 core electrons plus 2 electrons which are present as valence, or they are called as valence electrons. So no confusion regarding it. This is nothing but valence electrons that we call. These 2 electrons which are present. Hope it is clear now. No confusion. Same way aluminium, if you write, it is 13. So you write neon configuration into 3s2. After 3s2 which comes? See 1s2, 2s2, 2p, 3s, 3p, then comes 4s. So after 3s comes which one? 3p. Now you have to write 3p. Aluminium, so already 12, here comes 13. Now how many valence electrons are present in aluminium? You will have to see apart from core electrons, the other electrons present. Remember, these are the indication of electrons. These are principal quantum numbers. So how many electrons are present in aluminium? Valence electrons, 2 plus 1, 3 valence electrons are present. Clear? So this is about writing electronic configuration. I'll tell you about the stability. So if you remember this trend, in the next video I will be explaining you how actually there can be some changes in the trend. Though it continues in the same order, if you remember the atomic numbers, then you can go on writing the electronic configuration. But at a point you see that there can be change in the order also. There can be exceptions also. Which are they? That we will be studying. Okay.